Today we'd like to continue learning about heat. So in our last lesson, we saw that heat was just another form of energy, and that kinetic energy, electrical energy, and all other types of energy could be converted into heat. We saw that heat and temperature were different things. Temperature was a property of the material, where heat was just a process of adding energy to the material. Oftentimes they go hand in hand, so that when you add heat, you will have an increase in temperature. We'll see today that that is not always true. We learned the different conversion formulas for temperatures. It probably would be a good idea to put these on your conversion sheet, your green sheet with all your other conversions. We saw that when you had a delta temperature, you could work in Celsius or Kelvin, but not Fahrenheit. We reminded ourselves of the power equation, and we learned how to calculate heat. We learned about this specific heat column. We saw how it told us how many joules it took to raise the temperature by 1 degree Celsius for 1 kilogram of your material. We saw bigger numbers were harder to change the temperature of. We had a formula. Heat equaled specific heat, mass, delta temperature. Remember, this can be in Celsius or Kelvin. Delta temperatures are the same in both units. Today I'd like you to learn about phase changes and heat. With phase changes, we are no longer going to be changing the temperature as we add energy. Instead, we're going to be changing the phase of our material. So the first phase change would either be melting or freezing, depending on if we are adding energy or removing energy. So the question is, how much ice can I melt with a certain amount of energy? So we have the ice already at 0 degrees Celsius, so it's about to melt, but it will not melt unless we add more energy to it. It turns out we have a column on our reference sheet called heat of fusion. It's going to be abbreviated HF, and that is going to tell us how many joules are required to melt 1 kilogram of your substance. So if I want to melt 1 kilogram of ice, it would require 334,000 joules of energy. Obviously, if I only wanted to melt a gram, I would divide this by 1,000, and 1 gram of water would require 334 joules in order to melt. Again, the bigger the numbers are, the harder it's going to be to melt that substance when it's already at its melting temperature. So if I asked you how much ice can I melt with 1 megajoule of energy, we would write our formula, which this time is Q equals M times HF. You'll notice there is no change in temperature involved because our water is already at the melting point. We make sure we put our energy in joules, so a megajoule would be 1,000,000 joules. We're trying to figure out how much ice we can melt. And then we go back and we look at our heat of fusion for water or for ice. Obviously, they're the same thing. And then we would solve for mass, and that mass would be in kilograms. If I wanted to find out how much energy was required, again, I'd use the same formula. I'd use the same heat of fusion. I would get my mass into kilograms, so 4 ice cubes, each with a mass of 125, would be a total mass of 500. Make sure you put it into kilograms and solve for heat. Next, we want to look at boiling and condensing. This time we want to know how much energy is required to vaporize our water. This time the water has to be already at 100 degrees Celsius, and then the water will start to vaporize. It will start to boil. It will turn from a liquid into a gas. This time we look at the heat of vaporization. That's going to be abbreviated HV. And again, it tells us how many joules are required to vaporize 1 kilogram of our substance that is already at the proper temperature. So for water, it would take 2,226,000 joules of energy to vaporize 1 kilogram. Again, if I only wanted to do a gram, I would just divide my number by 1,000, and it would take 2,260 joules to vaporize just a single gram of water. Bigger numbers, again, require more energy to vaporize. So the formula this time is going to look the same as it did before, but instead of heat of fusion, we write heat of vaporization. Plug in your energy, plug in your value, solve for mass. I'm going to leave that to you. Again, if I want to know how much energy is required to boil away a certain amount of water, I remember that water, and only water, a milliliter is a gram. So this would be 500 grams, which would be half a kilogram. I put in my heat of vaporization, and I solve for Q. You should be able to finish this without any issue. So here are the 3 formulas, depending on what you're doing. If you're changing the temperature of your substance, use the formula from the other day. If you're changing the phase, use one of the 2 formulas listed below. Final thing I'd like you to learn today are phase diagrams. These show the temperature of your substance when it's in different phases based on how much energy you've added to your substance. So when you see these, the diagonal lines represent pure phases. So A would be a solid, C would be a liquid, and E would be a pure gas. The plateaus represent transitions. That would be the transition from solid to liquid, which we would call melting. Very important to realize that when the substance is melting, the temperature is not changing. All of the energy that you're adding is going into breaking the bonds that were holding the substance together. So in region D, you're breaking the bonds that were holding the liquid together, and it's turning into a gas. Notice this is not water because our boiling point is not 100. Our boiling point is going to be 20. So this is some other substance. The 15, the negative 15, is where the first plateau happens, and that would be called the melting point. So when you look at these graphs, you should be able to find the melting and boiling points, and you should be able to know each of your phases. Okay, so when you're looking at our equations, our first formula would work for region A, C, and E. They're the phases where we're changing temperature, where we are rising in temperature as we add heat. The other 2 are for the plateaus. So the heat of fusion would go for the melting, and the heat of vaporization would be for the boiling plateau. All right, so here are our different formulas one more time. And you should remember this column is the specific heat, this is the heat of fusion, and this is your heat of vaporization. Finally, we have a cooling curve. This is where we're taking energy away from our substance. So in this case, the heat is actually negative, although we don't represent it that way. We just realize that we are removing energy from our substance. So the highest temperature is a gas, which is now letter A. C is still liquid, the medium temperatures, and the lowest temperatures are where you are a solid. Region B used to be boiling. The reverse of that is condensing. And this used to be melting. This would now be freezing. Notice that the temperatures are the same as they were before. The freezing point will always be the same as the melting point. All right, so these are your big ideas from today. All you're doing today is taking notes and giving me a picture of your notes. I hope this was all clear. Have a good day.